Hello everyone, this is our Chapter 3 Dynamic Routing Walkthrough. Now this is going to be an awesome chapter because it's a big intro to what we're going to see in the future chapters. And here we're going to introduce dynamic routing protocols, which there's tons of them. We have OSPF, EIGRP, RIP, ISIS, and even BGP. But we don't have to go through all those. We have to focus on just a couple. So let's get started. For today, Chapter 3's main focus is on the basic routing protocol of RIP. Now, RIP is really underutilized because no one likes it, I have to say. It does not scale well, and is really not covered on the certification exams anymore. So why is it here? Because RIP is a very basic dynamic routing protocol, and it gives us the good understanding of how they actually work. So it's the simplest routing protocol of them all, so let's talk about it today. So we'll go through dynamic routing protocols, we'll go through RIP, then we'll even rip apart the routing table on a router. So dynamic routing protocols themselves, they've been around since the 1980s. Seriously, the 1980s. Now, newer versions of our routing protocols do support IPv6. They have been updated. So we see RIP version 2 was the latest IPv4 version of RIP. Then we have RIP NG. And raise your hand if you're a Star Trek fan. Raise it. If you're a Star Trek fan, RIP NG was actually based off of the name RIP Next Generation, which did come from Star Trek. So we have the IPv6 form of RIP, then we have EIGRP, OSPF version 2, ISIS, then we have their IPv6 counterparts. BGP we will be getting to in a later course. BGP is the Internet Routing Protocol used across the world. We're not going to configure the entire world, but in a later course we will have to be able to hook up our business sites to the actual Internet. Continuing on, why do we use dynamic routing protocols? Well, we came from Chapter 2 where we saw static routing with default routes and floating static routes with both IPv4 and IPv6. Now, IPv4, IPv6 static routes sounds like it wasn't too hard. Pretty easy. But that's when you're using smaller networks. It doesn't scale well. So as our networks start to grow and we have multiple connections to reach this exact same destination network, multiple ways to go, how do we do it? Static routes would be a major pain. It would scale horribly. So we deploy what are called dynamic routing protocols. And dynamic routing protocols are really services that you activate on your routers. And then when you turn these services on and you do a basic configuration for these services, now the routers on their own can talk to other routers. On their own, they can discover new networks that come online. They can keep their networks and their routing table up to date. And when there's multiple pathways to reach the same target, on their own, they can choose the best way to go. So how does this all work? Well, it's going to work utilizing three items that exist within our dynamic routing protocols, within all of them. So within OSPF, within EIGRP, within BGP, our complicated, complex, big, beefy routing protocols, they all have these three components. RIP, the simplest routing protocol of all, actually doesn't have all three, but that's a story for another day. So let's focus on these three components that actually make our dynamic routing protocols work. Every single routing protocol that we're going to go into is going to have a data structure, and a data structure is just the tables and databases that exist within RAM. An example of a table would be the routing table. The routing table of your router is a data structure that exists within RAM. When your router loses power or it gets turned off and turned back on, we don't want to retain the routing table. Because by chance, if one router went down, most likely there's probably another that went down too. And if you just want to come back online and say, I expect all the paths and all the destination networks to still be exactly the same, even after a failure, So that's kept in RAM, so it will be wiped. Also with our tables, we have other tables too that are very cool. We have neighbor tables. Neighbor tables include what are called adjacencies. Routers can track each other using their routing protocol. They'll know if the neighboring router next to them is up or if it's down, the speed of the link, the type of link that they're connected on, and even what their neighboring router knows about with its neighbors. We even have topology tables. With routing protocols like OSPF, a topology table is an entire map of the entire network. It is so cool. And these are all part of the data structures that allow our routing protocols to work. Static routes, nothing like this. In order for our routers to talk, the next item is routing protocol messages. With some of our protocols, we're going to see hello messages. We're going to see update messages, acknowledgement. We're even going to see some crazy messages known as queries and replies. That'll be up and coming with other routing protocols. But all these messages exist so our routers can keep each other up to date. They can see if the neighboring router is even alive. And they can even call out and shoot a flare up in the sky because your router is sinking and dying because it doesn't know how to get somewhere. And your router can actually shout on the network for help with a query message. We'll see that with EIGRP. So lastly, in order for all of this to work, we mentioned that our routers can see the destination networks. Then they can find the best path to reach a destination network. Well, how do they find the best path? They're going to have to do some calculations. So every routing protocol has what's called an algorithm. RIP has an algorithm known as Bellman-Ford. OSPF has an algorithm called SPF. And EIGRP has an algorithm known as either dual, DUAL, or also known as Dijkstra. It depends on what you want to go with. The name of the algorithm or the name of the creator, they use both. So the algorithm is just a mathematical formula that allows you to find the best path to reach a target, especially when there's many ways to reach the same destination. Your router handles it all. So we've seen static routing in Chapter 2. So quick recap, static routing does have a use. It's not just, well, it doesn't scale well, why do we ever use it? The default route usage of a static is the most common usage of a static route. That quad zero send all traffic to any network this direction. Also, when we have stub networks, a stub network is just a network that has one way to reach everything else. And that's just you have an uplink, a single one, that takes you to the rest of the network, or you have an uplink that takes you to the internet, that would be your stub network. And again, it doesn't scale too well, but it is great and easy to deploy. When you're studying for certification exams, there is an extra item on here that we do want to mention. Static routes are considered very secure. And it's kind of a weird thing to say because people are like, well, how is it secure? It's a static route. Well, compare it to dynamic routing protocols. As we mentioned, dynamic routing protocols use routing protocol messages, which means there's actual messages going between the routers talking about the networks that exist and where they're located. If someone were to hook up a sniffer machine, like maybe a little Wireshark box, and be able to take a look at the network traffic, they can actually open up and rip apart the routing protocol messages and gain info about the network. Also, if routing protocol messages are accidentally going down from a router to a switch to where the PCs are located, a user can bring a router from home that they got on Craigslist or eBay, plug it into the network, and start receiving routes, and then possibly even start injecting bad routes back into the network. You can't do that with static routes, but with dynamic routing protocols, you can manipulate those messages in multiple ways. So know that it's considered very secure for static routing, because that's on your cert exam. Continuing onwards, we've seen static routing, we've seen when and how to deploy, and for this type of topology, it's beautiful. Router 1 is considered a stub. Router 1 has 3 directly connected networks, and it knows about all those in its routing table just because they're Cs. They're directly connected. So Router 1 just has to send the rest of the network traffic over to Router 2. So Router 1 just needs a default route. Default route, send all traffic I don't know how to get to Router 2. Router 2 then has a default route out to the web, which is the internet. Router 2 knows about the 3 networks it's directly connected to. So what does Router 2 need? It's fine, it's done. No, it's not done. Router 2 is the default route to the web, and it knows those 3 directly connected networks. Router 2 does not know about the 192.168.10 and the 192.168.11. Those are considered remote networks for Router 2. So if we're doing static route deployment, Router 2 would need 2 static routes. One to target the 10 network by going to Router 1, and another static route, the second one, targeting the 11 network going to Router 1. So for this entire topology, we'd really need 4 routes. Default route from Router 1 to Router 2, default route from Router 2 to the internet, and then 2 static routes specifying the 2 subnets of 10 and 11, targeting Router 1. So, when do we use dynamic routing then? Because static routing, we could do that. We could do it all day. It's not too bad. It might take us a couple hours for this topology. So, in this type of scenario here, this is where we actually would want to take a look at deploying dynamic routing protocols. We have multiple pathways to reach the same destination network, and as paths go up and down, I don't want to be driving into the office at 2 in the morning. I'd rather have the routers fail over on their own. So, hey, check this one out. As your scenarios get more complicated, this is when we really want to make sure we're using dynamic routing protocols. Here we can see multiple regions interconnected with many different pathways to reach a same single target. And you want your routers to be able to handle that. You want the routers to be able to talk to each other. You want the routers to be able to stay up to date and be able to find the best pathway through all of these links. And the routing protocols can do it. So the overall advantages of dynamic routing protocols. When you've got multiple routers and multiple pathways, beautiful. These things can adapt automatically as pathways go up and down. So they'll find the best pathway right now, and in 5 seconds, if a router in the pathway goes down, your routers will route around it. It's gorgeous. Now the disadvantages though, because you're turning on a routing protocol, it's not just flip the switch and we're done. There's actually configurations that can get a little complicated, so they can be complex. Also, as we mentioned, static routes were considered very secure. Dynamic routing protocols, they're considered less secure. There are additional configs we can put on our dynamic routing protocol messages to utilize things like authentication to authenticate the source of routing protocol messages, so you don't just trust any message that hits your router that says, I'm a routing protocol message, listen to me. Well, you can actually utilize authentication to authenticate who the source is of that. Some of the new protocols coming out as well will include encryption, where you can have encrypted routing protocol messages, but that's still in the works of being deployed. On top of all this, when we talk about routing tables and data structures, when we talk about routing protocol messages, when we talk about routing protocol algorithms, all that stuff does not come free. And what I mean by that is the routing protocol algorithm, that math formula, it uses the CPU. It's going to churn through your CPU to make sure you're using the best routes whenever there's a failover. That's going to hit your CPU utilization. When we talk about the routing table structures in the database, such as having a routing table, a neighbor table, a map of the entire network known as a topology table, that's going to take space in your RAM. So you're going to have some RAM utilization just based off of that. And on top of it, with routing protocol messages, your routers are generating messages just to talk routing protocols with other routers. With EIGRP, there's even an interface command. It's IP bandwidth percent. And the point of this command on the interface in EIGRP is to be able to limit how much routing protocol traffic can be utilized against the entire bandwidth available on that interface. For example, you can specify the default of 50%. By default, EIGRP, that routing protocol, is allowed to use up to 50% of your interface bandwidth. Now, it's not going to be 24/7. There will be spikes with these routing protocols, and then they'll be quiet. We'll see that up and coming as we go through the chapters. Just keep in mind that dynamic routing protocols, they will take a small hit at minimum against your equipment. Static routes, you set them and you're done. They're not recalculated over and over again. But dynamic routing protocols, there's always calculations, there's always entries exiting and being put into your tables. So as you go through the reading, please make sure you do these activities. Here's my screenshot of the static routing versus dynamic routing comparison. Go through these because these will help you for your final exam, and also they're really going to help you for the cert. So again, as you go through the course reading, please make sure you can answer the questions in the tables. So we're more than a third there. Let's keep moving through. Take a break if you want, because you can pause. And let's hop into RIP version 2. Now this topology looks easy. It is really easy. We've got router 2, which is in the middle here, and then router 1 and router 3. If we wanted to talk static routing before we do RIP, a quick conversation. Know what you got. Router 1 has two interfaces directly connected, so router 1 knows how to automatically reach the 1 network and the 2 network. So what does router 1 not know how to reach? Well, router 1 doesn't know how to reach the 3 network, the 4 network, and the 5 network. So we go to router 2. Let's talk about it. Router 2 has 3 directly connected networks, 2, 3, 4. Router 2 needs to know how to reach the 1 network, which is remote, and then the 5 network, which is remote. Lastly, router 3, directly connected to 2 networks, the 4 and the 5. Router 3 has to remotely reach the 3 network, the 2 network, the 1 network. And by reading this topology and understanding that, now we can build static routes, because you know what you got to reach. But in this scenario, let's go dynamic routing protocol. Let's say, you know what? How about I just have router 1 turned on for RIP, and router 1 will tell router 2 what it has. Router 1 will say, hey router 2, I've got the 1 and 2 network. I thought you should know. And then router 2's got 3 networks. Router 2 should tell everybody it's got these 3 networks. Hey router 1, I've got the 2, the 3, and the 4. Thought you should know. And lastly, router 3 has 2 directly connected networks. So why not have router 3 tell router 2, hey router 2, I've got the 4 and 5. Thought you should know. And that's exactly what we're going to be doing here with these dynamic routing protocols. We're going to go on these routers and activate their ports for this dynamic routing protocol. And then the routers will share the networks that exist on the ports. Not too bad, right? And you're like, cool, this is awesome. There's no like IP route crazy statement. It's just, I'm router 2, this is what I got. Thought you should know. And that's what dynamic routing protocols really is all about. So when we configure this in the next 2 slides, keep that in mind. You go on your router, and now with dynamic routing protocols, you don't specify where you want to go. You specify what you got. So then you can share it. It's like 2 neighbors standing in their backyard talking over a fence. Hey, Tim, my neighbor next door, standing at the fence next to him, chatting over the fence. I know how to get to the plush horse ice cream shop. I'll give you the directions. Thought you should know. And Tim's like, awesome. I know how to get to Mariano's where you can go to the hot food bar. Thought you should know. Like that type of scenario. It's not, I want to get somewhere, let me create a route for it. You're just sharing what you know. And with routers, what we know is what we're directly connected to. So let's continue. How do we use this dynamic routing protocol of awesome power? And that's very simple. RIP is the first dynamic routing protocol we talk about. Again, it's not CERT content here. It's not heavily used in industry. You can see it on some Soho boxes even. RIP, the main reason we don't use it, doesn't scale past 15 routers. Also, it's got a horrible update timer that we'll see in the next slide. It's annoying. That's about it. So let's talk about it. To do RIP, we go into our global configuration mode, which is config T, and then we type router space RIP. And once you do router RIP and hit enter, you're in RIP mode. You're now in config-router. Any command you type is within the RIP protocol now. Hooray! Awesome. So they hit question mark, and we can see there's tons of commands down below here. Now, we're not going to focus on the commands in white because no one ever knows every single Cisco iOS command. It's not feasibly possible. Even triple CCIEs don't know every single Cisco iOS command. You know what needs to be utilized for a topology. That's what it comes down to. So for us here in CCNA, we're going to focus on auto summary, default information, the network command, which is the most important of this entire chapter, passive interface, and version. And we're going to hop into these. So we'll start with the network command. The network command is the most important for this entire class right now in this course here. We're going to use the network command for multiple routing protocols. This network command does the exact same thing regardless of the routing protocol you're using for EIGRP, OSPF, or RIP. So what does it do? Well, it does two things. What we're going to do is we're going to go in router 1. And in router 1, we're going to say network followed by the exact network that we have on the left link. Enter. Network followed by the exact network we have on the right link. Enter. And the two things it does. Item 1. When you use the network command, router 1 is going to look for an IP address on your router. And the IP address that matches or falls into that network statement, that interface, is activated. Let's say that again. When you type a network command, your router then looks at the interface IP addresses. And when it finds an interface IP address that falls into that network that's here, that interface is activated for RIP. So gig00 is now activated. Now, this slide has a horrible thing that Cisco put in that I do not like, and that's the second statement. The second statement is not it advertises the specified network. What that really happens, real world Cisco, is the network that's on the interface. The network on the interface is what is then shared in your routing updates. So when you say this network command 192.168.1.0 and you hit enter, the router says, I'm going to say this is a classful equivalent /24. RIP assumes classful, always. 192.168.1.0, that's a 192. So obviously it's a classful /24. I will look for anything 1.0 up until 1.255. And if I find any interfaces that fall on 1.0 up until 255, I will activate those interfaces for RIP. And now RIP messages start to flow. And that's item 1. Then we have item 2. So let me change my color. And with item 2, item 2 is any interfaces that were activated for RIP. I will now take the network on that interface and I will share that network in my RIP updates. So this is the most important part. Please rewind and watch this again because this network command gets really confusing. And let me show you a confusing example after you rewatch this section. So hopefully you rewatched it. Confusing example is right here. So what I want to show you is this. What if it wasn't a /24 here? What if this was a /25? Now this is a /25, 192.168.1.0. That's cool. So let's take a look at what's going to happen. When I say network 192.168.1.0 inside of my config still, the router assumes /24 because it assumes classful, and that's what a 192 is, a /24. Now when we say this, the router says, all right, I'm looking for 1.0 up until 1.255. I'm looking for any ports that use an IP address in that range. So it looks through and it says, oh look, I found a 192.168.1.1. So it activates gig00 for RIP. And now we're not sharing 192.168.1.0 /24. This network statement is not what we're sharing with other routers. As mentioned with item 2, what we are sharing with other routers is going to be the exact network that exists on the port activated. So we would actually be sharing with other routers 192.168.1.0/25. And you're like, okay, kind of getting it. Think I'm getting there. Well, let me show you one more example. What if we had another network that existed on router 1? What if on router 1 we had another port here, and this port, let's say, was 192.168, and let's say it's going to be 1.128/25. 192.168.1.128/25. And you're like, well, Justin said use the network command for the exact networks you're connected to. Well, if you did network 192.168.1.128 and hit enter, guess what's going to happen? The router is automatically going to turn this to 1.0 in your config. You can type network 192.168.1.128. You can hit enter. The router will take it. No error message. But in your config, the router will convert this to 1.0 because it only understands classful with these network statements in RIP. And then, well, how would it share the 128 network? It just does. 192.168.1.0 is what would go in your config. And again, 0 up until 255. It'll look for a port using one of those IPs. 128 exists in that range. So that port would be activated for RIP. And then item 2, the network on that interface is then shared. We'll do a lab walkthrough together a little bit later if it's still a little rusty. Just keep in mind, this network command, you're typing in a range. If I say network 192.168.1.0 enter, now any port in that network range that has an IP address that falls on it will be activated. The network could be a 1.64. The network could be a 1.192. But as long as the IP address on that port falls in the network range here that's classful, that port's activated. And then the network on the port is what's shared. As these shared networks go around, they're sent every 30 seconds. Every 30 seconds for the life of the router, it could be 30 years later, every 30 seconds that same update goes out saying, I'm router 1. I have these networks. Even if nothing's changed, router 1 is very chatty. So to verify that this actually works, we have a bread and butter, awesome, amazing command called show IP protocols. Show IP protocols gives you not just RIP, it gives you everything. So if you're running OSPF, BGP, EIGRP, ISIS, or anything routing protocol wise, it'll show here. So we do the show IP protocols command. It shows us that we're running RIP. We can see our timers. RIP sends updates every 30 seconds. The next one is due in 16 seconds. It's going out. After 180 seconds, which is 3 minutes, if we haven't heard about a route from a neighbor in 3 minutes, we declare the route is invalid, as in we can't use it. The person who gave us the route, I think they're dead. They're not talking, so we're not going to send traffic to them. We'll mark the route they gave us as invalid. After 1 more minute, which is 240 seconds, 1 minute after the invalid timer hits, then we can actually flush the route from the table. Like, well, why the invalid versus the flush? It's easier for us to take an invalid route and mark it as valid if we hear an update about the route. It's harder for us to bring a route back into our table if we flush the route, which means delete it from the routing table. That's the difference. So we give ourselves 60 seconds extra time before we actually delete the route from the table to have the route be saved. On top of that, we can see the actual interfaces that have been activated for RIP. We can see that we're sending RIP version 1 messages, and for backward compatibility, we can receive version 1 and the newer version, version 2. Like, how does that work? If we're sending version 1, how can we be listening to version 2? Because you can understand part of a version 2 header, but not all of it. Really, you pull the version 1 components out of a version 2 message. Like, I got that part. I don't understand the rest of what he just said, but at least I understand the basics of the version 1 part of his header. Automatic summarization is horrible in every routing protocol. Automatic summarization can cause inconsistent routing. Really, really, really bad. The best thing we can do is always turn off automatic summarization. Down below, we can see the network statements that are typed in. These are the classful statements. I hate this part. This is routing for networks. That is such a lie. These are not the exact networks you're routing for. These are the classful network statements that are utilized to activate your ports. Remember that. Item 2 and that little weird nuance. Down below is the second most important part of this entire output, and that's the RIS. routing information sources. This is a neighboring IP address of a router that you're learning routes from. If you don't have any routing information sources, nobody is sending you routes and your routing table is dead in the water. Without a source, you've heard nothing. So we can see 192.168.2.2, that's actually router 2. They're sending us updates. The last update was 15 seconds ago, and we see the administrative distance of RIP, which is 120. Like, why is it listed twice? Because in CCMP route, we'll teach you how to change it. We'll modify and rig elections, and we'll rig many things with administrative distance. So, here it is. Our networks are activated. How do they do this? Well, they went on every single router, and they went say router 1, network 192.168.1.0. Router 1, network 192.168.2.0. Then they went on router 2. Same thing, network 2.0, network 3.0, network 4.0. Individual network statements activated RIP on every port. Then they went on router 3, and they did network 4.0 and network 5.0. And router 3 shared what it knew, router 2 shared what it knew, and router 1 shared what it knew. And now router 1, check it out, it's got R's in the routing table. Remote networks that we know how to reach. Beautiful. If we take a closer look, we'll see router 1 knows how to reach the 3 network, remote, the 4 network, remote, and the 5 network, remote. We'll see the administrative distance, which is the trustworthiness of RIP. It's 120. That's actually really bad, but that's what it is because RIP is not a good routing protocol. Then there's that little number after it. That's your metric. And with RIP, that's a hop count. This is like Chutes and Ladders, or if you played the game Sorry. What happens here is with that number 1 and 2 that we see, this is the metric of how far away it actually is to reach the destination target. For router 1 to reach the 3 network, it is 1 hop and then slide. In order to reach the 4 network, it's 1 hop and slide. So that 1 is just a 1 router hop away and then slide to reach the 4 network. To reach the 5 network, we actually have 1, 2 hops and slide to reach the 5 network. So you see that metric of 2. RIP is very basic and very dumb. That metric sounds so nice and easy for us, but it doesn't care about bandwidth. It doesn't care if it's a 56K link or if it's a 500 gig link. It doesn't care. It just says it's 1 hop away and slide. So again, RIP is not a good routing protocol to use in enterprise, but it's nice to train and practice on. So we have RIP version 1 and RIP version 2. What is all that about? Well, RIP version 1 is really basic and really old. RIP version 1 uses broadcast technology, which is the all255 targeting address for any updates. Yeah, and that's bad. RIP version 2 uses multicast, so people tune in to listen to messages for RIP when they need to. Also, RIP version 1 does not include classless subnet masks. RIP version 1 is classful only with routing updates that go left and right. RIP version 2 actually includes classless masks, and RIP version 2 uses multicast like I mentioned. So we always activate RIP version 2, and that's our main usage. Even though we're running RIP version 2, it still uses a 30-second timer every 30 seconds, regardless of change. So we mentioned auto summarization, and I told you it is bad. EIGRP also uses auto summarization, and it's turned off now by default in the latest release of it because nobody likes it. And in RIP, we have auto summary. But sadly, in RIP, auto summarization is on by default, so we need to turn it off. And that's really simple. Inside of your configuration for your config-router, that's after you do router RIP. After you do router RIP, just type no auto summary, put it in once, and now your router will not automatically summarize. Again, we don't want a router automatically summarizing for us because it's going to create summary statements of networks that you might not have. And also there's problems where you can have something called discontiguous networks, and we'll talk more about that later as we go into EIGRP and OSPF. I'll teach you how to avoid that. Now we mentioned that when we use the network command activates a port, so now we have RIP activated on a port sending routing protocol messages, but then the network on that interface is also shared with other routers. Well, item 1 of this, the port is activated for a routing protocol and the routing protocol starts sending messages. We don't like that when the port is connected to users, like in this case, or in this case, or in this case. So how do we stop our routers from sending routing protocol messages down to users? Because that's wasting the bandwidth of our links. It's wasting the resources of the CPUs and the switches receiving traffic that they just throw in the garbage can. And also it's a security risk, because if people use a tool like Wireshark, or they bring routers from home that they got on eBay or Craigslist, now they can put their routers and have their routers talk with your routers. and their routers aren't supposed to be on the network. So how do we stop this? And that's called passive interfaces. What we do is we go inside of our routing protocol and we use these commands multiple times. On router 1, if we want to say gig00, I understand we're using the network command. I understand that you're sending RIP messages now. And also I understand that your network is being shared with everybody else. I want your network to be shared, router 1. I want people to know about the 192.168.1 network. I want them to reach it. But stop talking to the users downstream because they don't want to hear it, and also it's a security concern. So what we do in router 1 is we use the command passive-interface followed by the port number. When you say passive-interface followed by the port number, this stops your router from sending and receiving RIP messages. Now the cool thing about this command also works in EIGRP, which we'll get to, and it also works in OSPF as well. Exact same command. But what if you had a router that had like 10 interfaces, and you had 8 interfaces that you wanted to go quiet? Well, there's a command called passive interface default. This is the most secure command you can run. The best thing you can do with a firewall on a PC, block everything and selectively allow. Well, that's what passive interface default does. With passive interface default, once you click enter, every single port on your router goes quiet for the routing protocols. It stops sending and receiving traffic for routing protocols. To bring up the ports individually, you would say no passive interface followed by the specific port number for each and every port you wanted to turn back on for routing protocol messages. Cool output, by the way, inside of your show IP protocols, you'll actually be able to see what protocols are marked as passive. Now, this is not just for security, this is also really good topic coverage for the certification exams. When you're troubleshooting your CCENT and CCNA, you will get topologies where a PC at one switch can't talk with a PC at another switch. And even though you're like, oh, it's got to be the PCs and the default gateway, you're like, oh, that looks fine, it can't be that. It may just be that router 1 might have an accidental serial port passive interface, or router 2 will have a passive interface it shouldn't have. Passive interfaces should not exist on ports interconnecting routers. Because if you take a port on a router that goes to another router and make it passive, guess what? You're not talking routing protocols anymore. So this is a great way to be able to get through an easy/difficult challenge on your cert exams. Difficult challenge on the cert exam, if you don't know to look for it, easy, because I told you. So look for passive interfaces in this output that should not be marked as passive in your cert exams. Now, we mentioned default routes in Chapter 2. They are awesome. We loved them because it send all traffic with any subnet mask over to a specific target. But how do we bring that into RIP? Because, RIP, there's no network default route. Well, there is, but that's CCNP route, and we don't talk about it here. Let's go with what we want to talk about. So in this case, router 1 has a default route, which is a quad 0 to the internet. We see it right here. Hooray! Router 1 can get to the web. But router 2 doesn't have a default route. We'd have to statically configure one going left. Router 3 doesn't have a default route. We'd have to statically configure one going left. And then if there was a router 4, we'd have to have a default route going left. And you get the gist of it. If you want to deploy default routing across the topology, you'd go in every single router, do a default route, and tell it where to go. Well, we have dynamic routing protocols. There's got to be a better way. Well, there is. On your edge router, the router that goes to the web, on router 1, we create the default route. After we create the default route, on router 1 we go into RIP and we have this super awesome command. This command works in both OSPF and in RIP. It is default-information space originate. And what this means, default information originate, default information, I will take the default route and I will be the originator of it. Like the originator of it. Think of it this way. Global config, you created the default route. You then went into router RIP, which means you went into the RIP factory. You walk into the doors and there's all these assembly lines and you have envelopes going across on these conveyor belts and they all say RIP on every envelope. And now you have this one person that says, we use default information originate. We are now the originators, everybody, of the default route. And everyone yells, hooray! And now they start taking the default route and shoving it into every single RIP envelope as it's going down the conveyor belt. We are the originators of the default route. And that's what default information originate means. So now what happens is we have the default route in our routing table, and this default route is now going to be shared through RIP to router 2. Router 2 will say, I have the default route now. It updates the exit to go left. Router 2 then shares the default route through RIP to router 3, who updates the exit to target router 2. Router 3 then shares the default route using RIP to router 4. And all the routers will now actually have an R star. Star for default route learned through RIP. Pretty darn cool. The only router that won't have an R star is the originator, router 1. He learned it through static, and static is better than learning it through RIP. Awesome. So take a break. You need it, and we'll come back and we'll go through section 3, the last section. So the last section is called the routing table. And with the routing table, we're going to be going into the routing table. Now you're like, how do we have a whole section on this? There's some interesting, air quote, terms that we're going to talk about here. And some of these terms are just for final exam usage. We're not going to use them in real life. There's one term we'll actually see on the cert exam out of all the stuff we're about to hit. So let's hit it. Routing table entries. First thing, this is a routing table. We see this is router 1's routing table. We have the default route. And then inside of here, check it out. We've got directly connected. We've got the local routes, which are the L's, the exact IP address of a port. We've got RIP routes that have been learned. But, there's some weird stuff in here. Like, let me take a different color. What is this weird stuff? Highlighter. What is that? What is that? 172.16.00/16. There's no letter in front. And look, there's another one. 209.165.200.0. Again, there's no label in front. There's no via. There's no exit interface. Like, what is that? Well, that's what we're about to take a look at a little bit more. Those are called parent routes. They're really not routes. They're kind of like labels, but they call them parent routes. We'll get to that in a couple slides. So, there's things about the table we don't know yet, and it's time to start learning them. So, from Chapter 1 and Chapter 2, I think we kind of got this down already. Wow, that's a very annoying laser pointer. But I think we kind of got this down. So let's keep moving through because, come on, there we go. So this is our routing table. We've got this covered. Also, we should be able to read our actual routing table messages already from Chapter 1. We talked about this. Then Chapter 2, you built them. So you should know how to do this. Let me know if you have questions on this. Activity time. As you read through a routing table, make sure you can actually decipher what it means. So when, for example, we say the route source, what's the route source for 10400/16? You're like, 10400/16. The route source is blah. What is it? It's S. S for static. So make sure you're going to do these drag and drops. And if you can't, please ask for help, tutoring, or me. Now it's time to learn the new lingo. The lingo that you'll be utilizing in tests. And mainly in tests only. You're not going to go to work and say, hey boss, check it out. Look at all the new level 2 child routes we have today. That's not going to happen. Also, you're not going to say, hey, supervisor, did you see the number of level 1 ultimate routes? Maybe we should supernet more. You're not going to have that conversation either. So we're going to use these terms today regarding some tests in the Cisco exam, and there's only one of them that we're actually going to bring up on the cert exam. But this is to help us better understand how a router utilizes the routing table. That's the whole reason for this entire section, is to help us understand how a router utilizes the routing table. We'll see that at the last slide. Now it all makes sense. So let's go into it. This is the routing table we're going to rip apart. Let's hit ultimate routes first. The ultimate route is the easiest one ever, and this is the one that's actually on our cert exams. Everything else is like poof, never saw it, never heard about it. The ultimate route is any route in your routing table that has an exit interface or a next hop IP. You're like, wait, any route in a routing table that has an exit interface or a next hop IP address. Or a next hop IP. Is that everything? And the answer is yes. An ultimate route is every single route in your routing table, except for these two. Sometimes it might be more than two. What are these? Well, I already identified these 2 slides ago. These are called parent routes, and we'll have a slide upcoming where we'll talk about these. But to break the great, amazing conversation early, a parent route is just a label on a folder. It's a label on a folder. That's all these things are. Items that do not have a via or an exit interface are called parent routes. Everything else is an ultimate route. So remember, an ultimate route is a route in a routing table that has a next hop IP or an exit interface. Very easy, very straightforward. So let's go deeper now into the terms. We have a term called a level 1 route. A level 1 route is one of the first routes that are looked at during a routing table lookup. With a level 1 route, it is a route that has a subnet mask that is less than or equal to classful. And like, that means absolutely nothing to me, Justin. I cannot relate. I understand. So let me explain. When you see a route in a table for a destination network, for example, of 192.168.1.0/24, a 192, this classful mask is a /24. So a destination network in your routing table of 192.168.1.0/24, that's equal to classful. So we call this a level 1 network route. A level 1 network route is a route that is a mask equal to classful. Well, what if it wasn't equal? What if it was a 192.168.0.0/16? Well, we know 192, the classful equivalent, is a /24. A 192 network statement with a /16 is less than classful. That's a level 1 supernet. Level 1 because the mask is less than or equal to classful. In this case, because it's specifically less than classful, it's called a supernet route. And lastly, a quad 0, where it's a 0, 0, 0, 0, 0, 0, 0, 0. You get what I mean. That's known as a default route, which is considered level 1, less than or equal to classful. So what I need you to memorize right now, ultimate route is a route that has an exit interface or a next hop IP, aka everything but a parent route. A level 1 route is a route with a mask less than or equal to classful. And then we have 3 versions of level 1 routes. The network route that has the exact mask for the classful equivalent, the supernet, which has a mask less than classful, then the easiest of all, the default route. So get these in your notes, pause the slide, and make sure that you can actually reference it for your exams. Screenshot. That's the best thing you can do right now. So, continuing onwards. Here's our routing table, and check it out. What is this? It's in orange. That has a subnet mask less than classful. 192 would be a /24. The mask in play is a /16. Thus, for it is less than classful. So what type of route is this? Pause the video and answer this question. Subnet mask less than classful. It is a supernet. It's a level 1 supernet route. Hooray. What is that guy? Static route. That is a level 1 default route. You're like, I got this. Why is this one in bold? Couldn't tell you. Accidental bolding in the slide. Continuing on. So we've mentioned it already, so here it is. There's things called parent routes. And parent routes are a little confusing at first, but I want you to think of as these are just labels. It's a label in a folder. Let's think of a router. We have a router, and my router is sitting on top of a file cabinet. And in this file cabinet, I take all these routes, and let's say each route is a piece of paper. And I'm like, all right, I've got like 15 routes. So let me just take my 15 pieces of paper, where each paper has a route and how to reach it, and I'm going to toss them in the file cabinet. Just open the one huge drawer here, and I'm just going to toss it straight in the file cabinet, all 15 pieces of paper. And now whenever the router wants to do a routing table lookup, it's got to sort through 15 pages of paper. Well, what if there was an easier way? What if I put folders in the file cabinet? And now, on the folder, I can put a label. That's exactly what parent routes are. Parent routes are labels on a folder. So what we see here is we have the label, which is classful. You'll notice that for every single parent route, they are classful labels. 172.16.00/16. This is a label on a yellow manila folder in the file cabinet. And in this folder, it says, hey, I've got anything 172.16. If it exists in the routing table, it's in my folder. In my folder, I specifically have 5 different networks with 3 different subnet masks. Come take a look. So when my router has a destination target, maybe to reach the 172.16.3.5 PC, when the router needs to reach that target, when it goes through the routing table, it's going to look at these parent routes first. It says these are parent routes. They're level 1 parent routes. They're exactly classful. 172.16.3.5. Does that fit in 172.16 anything? Why, yes, it does. Let me now look in the folder. And now it checks the folder and says, hooray, I found the network I needed to use. On another point of view, what if we needed to reach something like the 10.1.1.1? If we need to reach the IP address of 10.1.1.1, we take a look at the folder. Hey, does this go into 172.16 anything? No, it doesn't. All these routes that exist, the parent and the folder, are now ignored. Does the 1011 fall in the 209.165.200 classful range? No, it doesn't. All these routes can be ignored. So now to reach the 1011, I either am going to look at this route, a level 1 supernet, or this route, a default route. Instead of looking through like 15 some routes, folder, fail, and then 2 more possible lookups and I'm done. And this is the whole reason we talk about these terms now, is so we can see this happen. The parent routes are utilized when there's routes inside. The routes inside we're about to hit, those are child routes. A parent route that we just talked about is automatically created by your router when a child route exists. And you're like, wow, this is weird. Well, you can't be a parent unless you got a kid. And if your kid dies, this is really morbid, then you're not a parent. Wow, that's horrible. I'm so sorry. But that's the way that Cisco explains this. So you have a parent route and you have a child route. And if you don't have children, then you're not a parent. So if your child routes are removed from the table, your router will automatically remove the parent route as well. The parent route only exists to be a label to explain what's below. So what is a child route then? Well, we mentioned a level 1 route. And a level 1 route was when you had a mask, and that mask was less than or equal to classful. So the only thing left over is the opposite. A level 2 route, which is also known as a child route. Level 2 route, child route, they're one and the same. So a level 2 route is where you have a mask that's the opposite. And the opposite is just greater than, not greater than or equal to. A level 2 route has a mask greater than classful. So whenever you have a route in your routing table, and that route is greater than classful, like a 172, which should be /16, 172 with a /24, that's greater than classful. 172/28, greater than classful. Whenever a route has a mask greater than classful, automatically it's considered a level 2 child route, and automatically a parent route, which is a folder, is built for it. And the folders are always classful, and then you have all these masks with greater than classful you have all these networks with greater than classful subnet masks being put into those folders. It's just a way to organize your routes. So level 2 route is the same thing as a child route, so they just say level 2 child routes. They're one and the same. These guys, they're not parent routes. The existence of a child route causes the existence of a parent route, which is just a label on a folder. That's all. So hopefully I explained it pretty well to you. Go through the activity here and see if you can figure these out. Look at the actual statements that they're talking about and figure out which ones are parents, which ones are childs, and which one's the level 1 route, and drag and drop. So to close it all down then, just about 5 slides left. This entire section was about the routing table lookup process. And this is exactly how it's going to work. If we find a level 1 ultimate route, we're going to use that to forward the traffic. If the best path is a level 1 parent route, we're going to use that in order to hop into a folder. We'll find the child routes, which are the routes that exist within the folder. If we find the exact match in that folder, then we forward. If we hopped into a folder or there was no folder that matched for us, then we move onwards. We look for supernets, like those /16s, the /8s. The supernet is a mask that is less than classful. That was the supernet. So we look for supernet routes next then after the parents. Now, if we have a match with a supernet or a default route, we use it. If there's no match with a supernet or a default route, the worst thing in the world happens, and the router throws the traffic in the garbage can. Aww. So, what the entire process would look like, let me clear my screen again. And there you go. Ta-da. You can screenshot this, you can use this for testing purposes. But the key thing here is you have those ultimate routes. Exit interface, next hop. We have child routes, which are considered level 2 routes that only exist when a parent route exists. And then we're going to have supernets and defaults, which are both level 1 ultimate routes. So take your time with this stuff because it does get a little complicated. The hardest part of this entire chapter, though, it might be right here. When we deploy routing protocols throughout this class and throughout the rest of CCNA, and then maybe in your future studies in CCNP, there's a very, very huge topic that a lot of people never get. Some people don't get this until they get towards CCIE. We've mentioned AD, administrative distance. And let me give you an example here. Let's say I have a targeted IP of 172.16.0.10. That's the IP address in a layer 3 header that my router has received, and the router needs to reach 172.16.0.10. Now, let's say I have in my routing table at this exact moment, which is possible. In my routing table at this exact moment, I have the 172.16.0.0/12, and this network was learned through OSPF. Then I have the network 172.16.0.0/18, and this network was learned through static, manually configured. Then I have the network 172.16.0.0/26, and this was learned through RIP. And all three of these routes are in my table at the exact same moment because they're technically different routes. They're different network statements. So when I have traffic that needs to go to 172.16.0.10, and this traffic matches every single route, well, which one is used? And this is where we get this huge misconception that comes into play. People say administrative distance, OSPF, let me write it in green, OSPF has administrative distance of 110. Static has administrative distance of 1. RIP has administrative distance of 120. And what I've always been taught, Justin, is lower is better. You said AD is trustworthiness, and the lower your AD is, the better, the most trustworthy the route. So obviously, Justin, because Route 2 was a static route and it matches, we're taking Route 2. We're using that pathway. And here's the crazy thing. That's actually wrong. Completely wrong. Route 2 is not used. All three of these are in the table, but Route 2 is not used. What's actually used? The RIP route. But it has the worst AD of them all. It's the least trustworthiness. It's horrible on the trustworthiness scale. And yes, it is. So why does it win? Why does the worst route actually win? Because what we're talking about here is called longest match. I don't like longest match because it goes with the ANDing process, which I get, trust me, but speed and ANDing process doesn't go hand in hand for me. What I like to talk about is you have the most specific subnet mask. The most specific network and subnet mask combo is what wins. A /12 here, a /12, that's a huge network statement. That's really a summary statement. A /18 is just a little bit better than a /16. A /18 there is going to be 64 Cs. That's a big network statement. A /26 is an exact block size of 64 IP addresses. A /26 is a very specific statement. /26 is more specific than a /18, which is more specific than a /12. So when we say longest match, what we're saying is that IP address broken down into binary, ones and zeros, the network statement that it has the longest match from left to right in binary, that's the network statement that's actually utilized. So before administrative distances are looked at, the most specific destination network in your routing table wins. The most specific destination network in your routing table wins, regardless of administrative distance. So then people throw their papers up in the air and say, I'm done with this, nothing makes sense anymore. But then we just go with something very, very, very straightforward. If the most specific network statement always wins, then when is administrative distance used? Administrative distance and routing protocol trustworthiness is only used if you've learned about the same network through multiple sources. If we've learned about the exact 172.16.0.0.26 network through RIP, and we've learned it also through OSPF, and also through static routing, the static routing route is what wins. That's when administrative distance comes into play. When you've learned about the exact same network through multiple sources, then and only then is administrative distance in play. But if there's 3 different network statements, the most specific network statement wins. That's when we do not have administrative distance coming into play. AD only comes in play when it's the exact same network learned through different sources. So get this down now because you'll be above the rest, guaranteed. So shutting it down, last 2 slides. IPv6, we got to go through level 1 routes. We got to go through level 2 routes. We got to go through parent and child and ultimate and network and supernet and default all over again. Nope. IPv6, everything is classless by design. In IPv6, there's no level 1 parents, there's no child routes. Everything in IPv6 is just called a level 1 ultimate route. There's no folder structure. IPv6 was made to be clean and classless. So taking a look at an IPv6 routing table, you've already done this in Chapter 2, but here you can read through it again. The route source, how it was learned, the network you're reaching, administrative distance, the metric to compare, and then the via, how you're getting where you want to go. End of it all. When we start learning dynamic routing protocols more so, we'll see EIGRP, which is marked with a D. We'll talk about why that is later. That's dual, the algorithm for EIGRP, and just how it was learned and where we're going to get there. Make sure you get comfy with this stuff. If you haven't finished the Chapter 2 labs, now is the time. Chapter 3 is very quick, very straightforward. Get through the reading, let me know how I can help, and have an awesome rest of your week.